All right, here's the quick video for section 1.4 where we learn how to combine functions. There's really 5 ways to combine functions. The good news is the first 4 are easy. Here's the first 4 right here. When someone writes f plus g in parentheses with an x right here, they're saying this is a function. I know it looks like 2 functions, but it's not, it's just one. And this function, this one machine, is defined in terms of these 2 other machines. So you'll be told what this machine is and you'll be told what this machine is. And using that information, you can figure out what this machine is. But know that this is one function, but it just means this thing right here. So you can come up with that function. Same for f minus g of x, f times g of x, f divided by g of x. These are all just a single functions that are defined in terms of 2 other functions. A quick note on the domain. To be in the domain of any of these functions, you have to be in the domain of each of the parts of the function. That'll be different when we get down to composition, but with these first 4, you must be in the domain of either of the 2 parts. There's an additional criteria for this 4th one here, because this 4th one introduces division. And one of the rules for domains is we got to make sure you don't divide by 0. So we also have to make sure that the denominator here, g of x, doesn't equal 0. So when you're figuring out the domain of f divided by g of x, first make sure to be in the domain of this thing. You're a number, and you want to be in this domain. You better be in the domain of f. You better also be in the domain of g, and it also better be the case that when you yourself go into the machine g, what comes out is not equal to 0. And if you satisfy all 3 of those criteria, you, my friend, are in the domain of f divided by g of x. All right, the 5th and probably most interesting, most challenging, most whatever you want to make it way to compose or to combine functions is to compose them together. And that's when you see something written, try to write this a little neater, like this. Much like up here, this might look like 2 different functions, but it's not, it's just one. It's just one function. However, this one function, just like up here, is defined in terms of 2 other functions, f and g. And just like I have these kind of translations that f plus g of x really means f of x plus g of x, f of g of x can be written like this. And the reason function composition is more challenging than these guys is when you look at these, you know what they mean. When you look at this, it might take a minute to get comfortable with. But know that this is the translation for function composition that's kind of analogous to these translations up here. And when I have that translation, I can do some work. So let me work on this example. And actually, before I get to this example, let me do, maybe there needs to be a part 0 here. Say you were asked to find f of g of whatever number you want, 2 maybe, f of g of 2. A couple different ways you can do this. One way you could do this is by following this translation here. F of g of x equals f parentheses g parentheses x. So f of g of 2 would be this. And I claim you could figure this out. Maybe you didn't know you could figure this out, but you've seen in other math classes nested parentheses, and you kind of always work from the inside out. So the first thing you would do here is you would figure out what is g of 2, the innermost parentheses. You'd figure out what is g of 2, and you'd write that right here. So g of 2, I can figure that out because g of x is 1 over x plus 3. So g of 2 would be copy this thing, and everywhere you see an x, change it into a 2. G of 2 would be 1 over 2 plus 3, which is 1 over 5. So g of 2 is 1/5. So f of g of 2 is the same as f of 1/5. And f of 1/5 I can figure out because f of x is 1 over x. So this would be 1 over 1/5, which is just 5. So f of g of 2 is equal to 5. That's one way you can solve this question. There's another way you can solve this question. Probably a more clever way to solve this question, a more useful and a more powerful way to solve this question. And it corresponds with number 1 here. So what you do is, rather than kind of translate this and solve this from inside to out, you come up with the rule of this function right here. Because if you had a rule of this function, remember this is just one function. This is kind of treating it like 2 separate functions. But this is just one function. If you come up with the rule of that function, you can evaluate it. So I can come up with a rule for f of g of x. I could say that f of g of x is really just f of g of x, translated into this notation. And then g of x, I know what that is. That's 1 over x plus 3. It's given to me in the problem. So really, I'm just figuring out what is f of 1 over x plus 3. And you can figure that out because f of x is this, so you can use this blueprint, except instead of putting in x's, put in 1 over x plus 3's, and you'd get something that looks like this. Note that I just copied this function here, except instead of this x right here, I wrote this as the input, this 1 over x plus 3. This right here is the composite function. This is the rule of the composite function. It's kind of messy. I could algebraically simplify this to get just x plus 3, because I could view the top as 1 over 1 and then divide fractions by multiplying by the reciprocal, get x plus 3. So what I have is a rule for this function. F of g of x is a single function, and its rule is just x plus 3. So now if I circle back and I'm asked question 0 here, I'm asked to find f of g of 2. It's easy. F of g of 2, just copy this blueprint up here, except everywhere you see the letter x, write the number 2, and you get 5. Note this is the same answer I got up here. Hell of a lot easier to do it this way, but this is a lot more powerful because what I now have is a rule that'll give me the input for anything that I put in, even if that's an expression, whatever, a variable, as opposed to having to go through the steps like I did up here. So f of g of x is this guy. Find the domain of f of g of x. It's kind of an interesting question. What you need to know is for the domain of f of g, you have to do two things. One, first check domain of g. G, not f? Yeah, g. First check the domain of g. Two, then check the domain of the composite expression. I'll explain, hold on. The composite expression. And then 3, there is no 3. You never have to check the domain of f. Wait, what? So if I have a composite function f of g, the order that I write the f and g matter apparently, because to figure out the domain, I look at g, I look at the second one for some reason, and then I look at the composite expression, whatever the hell that is, but I never check the domain of f. That's true. So let me go through and do an example to talk. Let's do this example right here. First, check the domain of g. G is 1 over x plus 3. So from this first step, I would conclude that x cannot equal negative 3. Because negative 3 is not in the domain of this function. If you set x plus 3 equal to 0 and solve, you'll get negative 3. Put negative 3 into this thing, you'll divide by 0. That's bad. So when you're checking the domain of g, you exclude negative 3. Then you check the domain of the composite expression. When I say the composite expression, maybe I should draw that arrow somewhere else. I'm talking about this guy right here. Check the domain of that thing, not the domain of f, 1 over x, but of this thing. Well, there's no square roots here, there's no even roots, there's no division going on. There's nothing to exclude in this specific example. That's not always the case. So when I'm figuring out the domain of the composite function, the only number I have to exclude in this specific case is negative 3. There's nothing to exclude from the second one because nothing can go wrong with this composite expression right here. I don't have to look at f. Note that the domain of f, the number 0 is not in the domain of f. But that's not a problem. I can put 0 into f of g of x and get an output from it, which is kind of interesting. So when you're checking the domain of a composite function, these are the steps you go through. If I was going to write my answer to find the domain, it would be everything except for negative 3, which if I were inclined to use interval notation, I guess I could write something like this. This is supposed to be an infinity here. Everything, now it looks like a pair of sunglasses, is everything less than negative 3, and also, in addition to, or everything greater than negative 3. That's the domain of f of g of x. Two more quick things before I finish up this video here. F of g of x is not what I wanted to do here. So for part 3, let's find g of f of x. The point that I want to make in 3 is that function composition is not commutative. F of g of x is different than g of f of x. And to show you why, let's just do this exact same example. G of f of x is, we'll work from the inside out. F of x is just 1 over x. So it's g of 1 over x, which take this g of x function, and everywhere you see the x written, replace it with 1 over x. You get here. This thing right here is not the same as this thing right here, or this here. I can prove that to you by simplifying. I would get 1 over 1 divided by 1 over x plus 3x over x, which is 1 over 1 divided by 1 plus 3x over x, which is x over 1 plus 3x. This is very different than this guy right here. The reason why is because this one down here is g of f, and this one up here is f of g. And the order that you compose functions makes a big difference. So that's why you get a different answer here. Last thing I want to talk about before I call this video good is function decomposition. So the idea with function decomposition is if you have something like, I guess I'll do the same example I did in the long video. H of x is the square root of, I don't remember exactly what I did, but maybe we'll call this good. Somebody could tell you this is the answer and ask you what is the question. In other words, you could be asked to express h as f of g. So find two different functions, f and g, that when you compose them together gives you this is the answer. I don't have a great way to tell you how to do this. What I do is kind of a guess and check method. You'll kind of get the hang of composing, and when you get really good at composing, you'll be able to decompose. Let me tell you the answer, and then I'll show you why this answer works. If f of x is, and I say the answer, that's a bad idea because there's multiple answers. One possible answer would be this guy here. Because if you compose f and g, if you figure out f of g of x, if you take this and put it inside this, you'll get this. Right? F of g of x is really f of 1 minus x cubed, and f of 1 minus x cubed is the square root of 1 minus x cubed. So this function decomposes into these two parts in this way. Interesting thing about function decomposition is there's lots of different ways to do it. For example, f of x equals the square root of 1 minus x, and g of x equals x cubed would be another possible solution. Another possible solution, kind of a boring solution, a trivial solution, but it's a solution, would be this one. And there's lots of different answers you can come up with. That's the point I want to make on function decomposition. Not a great way to figure it out, but there's certainly a way you can guess and check your answers. And as you start to guess and check, you sort of make your guesses more educated, and it feels less of guess and check and more of kind of an art to figure out this idea of decomposition. Stop this video here.